happy birthday, and thank you for being a physicist working in mechanics and doing so much work that's not just creative and interesting, but I think really inspiring in terms of the imagination and the drive to get at the fundamental understanding of what's happening at these hidden interfaces, which is such a mystery. So thank you for pursuing mysteries of life and science. I want to talk to you about some work we've been doing on looking at radiant state friction effects, which you heard Chris Marone talk about at the geological scale, and I'm going to talk about them at the nanoscale. And I'm wondering actually if there is a laser pointer. I don't know if there's one up here, if someone has, or I can use, here's the stick. All right, the stick is here. This work was done by graduate student Kevin Tian, former postdocs Nitya Goswami and Chunyang Lee, and it's a collaboration with David Goldsby at Penn, formerly at Brown, and with Terry Tullis, where this work first got started, which is funded by the National Science Foundation. Now, in reflecting on, during this workshop, about sort of some of the, the work being done here, the work Jay's done, the work I've done, I've realized that, we've interacted, we've never worked together. I didn't work for you, we haven't collaborated, but we've crossed paths at many, maybe we're all working for you in a way. But I realized that actually the connections between my work, my career path and Jay's have been increasing with time. And I'm not sure it's just a random effect. So, I did my PhD in physics, and I was working on friction, but it was at the nanoscale. So kind of, some connection. But then in 2000, I started working on brittle fracture. I'd never done anything in fracture, and Jay's done all this work in fracture. I had a project on pattern formation in 2002. Jay's worked on pattern formation. In 2004, I started doing more macroscopic work. Jay's worked at the macro scale. In 2007, I moved to Philadelphia. He's from Philadelphia. And in 2009, I started looking at failure and fracture of amorphous solids. So there's been this increasing, this change. And I had this dream last night that I was telling Alan Needleman about all of this and saying, Alan, I'm becoming more like Jay. And he said, Rob, you have to admit it. You're converting. You're becoming Jayish. And looking at the career trajectories and all the work in this room, I think there are a lot of Jayish people in this room right now. And so what you have, we're from all over the world, and it's the Jayish diaspora. And thank you for creating the diaspora. So we've been looking at this effect, which at the nanoscale, to try to understand this macro scale behavior, which is seen in tabletop friction experiments, and it's seen in tectonic plates and as underlying earthquake motion. It's this, and this is what Chris Marone talked about this. You drag a block over a surface, it's going along with the friction coefficient mu, you stop, and it relaxes. There's some stuff going on at the interface, it relaxes, and then you start up again. And there's a peak at first, this direct effect, and then it settles down to a higher friction force than before, because, I'm sorry, this is the evolution effect that I'll talk about. This is the aging, and then there's this ongoing higher friction at a higher rate. This is for a higher speed, if you go to a higher speed. And this friction peak tends to go up logarithmically with the time that you are sitting in contact. So this aging is occurring as you're sitting in static contact. And Chris showed you this radiant state friction law, this empirical law that says the friction coefficient you'll get goes up with the velocity and also changes with the state theta of the system. So there's a rate effect here. This has some good physical basis. The faster you go, the less time you give thermal energy to help you go over energy barriers as you slide. So this is sort of a kinetic a barrier hopping type of term. But this evolution effect, this state effect, is much more empirical and subject to debate. And two manifestations of it are here. So the longer you sit in contact, the more your static friction goes up with your hold time logarithmically. And also as you slide, there's this running in behavior that happens, and that's this evolution of the contact. So we wanted to try to get at what is happening at this buried interface by using the tools we were familiar with, the atomic force microscope. We're nano people, and we work with these nanoscale microscopes. And it was a conversation with Terry Tullis saying, well, we don't really understand what's happening when silica is in contact with silica. We don't know if bonds are forming. We don't know if it's creeping. What's going on? So we thought we could maybe try to see at least what's happening at small scales as a starting point. So in case you're not familiar with the tool, it's a small scale tip. It gives us a single well-defined contact point, maybe a 10 to 150 nanometer tip radius. So a contact radius that might be less than 20 nanometers, maybe even just a few nanometers in size, which is an attempt to represent the contact points in a more complex interface. So you have nanonewton forces, nanometer length scales, hundreds of megapascals, even gigapascals of pressure. You can get to pretty high pressures and you can damage things, which is good if you want to look at these high sort of stress conditions. So it's a well-defined geometry. And it's actually, in a way similar to any friction experiment, including the ones in Jay's lab. You have a spring to measure lateral forces and displacements. You have a spring to control normal forces. You might have a feedback loop. So you just have force displacements that you measure through the motions of these springs. So a way to measure lateral force, a way to measure normal force. And this is the idealized, highly idealized picture. We want to understand what the friction laws are for these well-defined contacts. And that's a starting point to maybe understand what's happening macroscopically, where you're going to have multiple contacts. I mean, if you're talking about geological materials, even what's going on in Chris Marone's lab, there's granular materials. It can be heterogeneous. This is a very complex problem to scale up. And we do not claim that the things we see here automatically, immediately explain what's happening, but it's a starting point. Okay, we're trying to uncover what's happening at the buried interface. And we're particularly interested in this evolution effect. So what is happening with time as the surfaces are in contact? This, as Chris said yesterday, this evolution effect is fundamentally important because it is what allows unstable slip to occur. The longer things stick in contact, the higher the frictional stress can build up, okay, before it finally gives way. And if you didn't have this aging, if you didn't have this strengthening, you wouldn't have earthquakes. So the fundamental processes behind it are not understood, and extrapolating from lab scale, like Chris's experiments, up to geological scale requires this understanding. And so the goal is to get at sort of process-based, physics-based, and empirical relations to do earthquake modeling and prediction. So, okay, there's been historically this discussion about the origins of this evolution effect. You can decompose the friction force in a simple, this is a Bowden-Tabor picture that some of you may be familiar with. You have a certain true contact area, and there's a force per unit area required for shear to occur. So the two generic categories of mechanisms behind the evolution effect would be contact quality increasing, so this shear strength increasing, just intrinsically higher resistance to friction, or contact quantity increasing. Maybe plastic creep is occurring as you load this system. It gets larger with time, and therefore you get more contact area. There are experiments both for granular systems and for rocks that show both effects, and maybe they're both active. But there's been some debate that one might dominate over the other. So what happens at small scales? So we use an oxidized silica tip. We use a silica surface, so it's a silica-silica interface. We put it in contact and we slide around. And this is the experiment that we actually do, which mimics the macroscale experiments, including ones that Chris showed yesterday. So we slide to get sort of the contact moving and fresh, and then we stop. So we hold for some period of time, and then we start sliding again. So it's this very simple slide, hold, slide protocol. And these are some old results. This is from 6 years ago. This is what happens when you start the second sliding. So you've held for some period of time, and you restart the sliding. And the friction force versus position looks like this. You have static friction, so you stick. So lateral force builds up, and then suddenly there's a slip, and then there's kinetic friction. And we're going to plot this friction drop from the peak to the kinetic friction force for various hold times. So if we just held for 1/10 of a second, it's a little bit of a drop. If you hold longer, you need to pull harder. There's a higher static friction. Higher yet at 10 seconds, higher yet at 100 seconds. So we see very dramatically this growth of the static friction force with the hold time. And plotting it logarithmically, it's approximately, you can fit it reasonably well with the log of the hold time. Okay? And we explain this mechanism by attributing it to chemical bonds occurring with time. And I won't go through all the arguments in the control experiments, but we were able to rule out plastic creep in our experiments. We could image the tip before and after. We could do a bunch of control experiments, and I'm happy to go into those. But for the sake of time, what I'll just emphasize is we see it on silica, where there's a chemical pathway for these bonds. We don't see it on diamond or graphite or other materials where there is not the same chemical pathway for bonds. And this is that chemical pathway. If you have hydroxylated silica, when you push it together, you can break a hydrogen off of one oxygen group, an OH off of another, and you can get a siloxane bond. This is called the condensation reaction. Water is the product of this reaction, and this is known as a very common reaction that leads to aggregation of silica particles. It's used for bonding wafers together in semiconductor processes. It happens with rocks. It happens in many different oxides, especially in silicon oxide. Yes? Yeah. So we don't see it. We don't have a way of measuring it, but others have measured it in macroscopic experiments, and you see it as a product. Yes. Spectroscopy has established this very nicely. Yeah.
Is this done under vacuum?
So our experiments are not done under vacuum. They are done in, we can go to very dry conditions with nitrogen atmospheres, and there's actually a humidity dependence to this effect. So it will happen in air. Yeah. So this is a picture from Isabellas Lufarska's group where they do reactive molecular dynamics. They also do quantum chemical calculations. So you bring two silica surfaces together. So here's an OH here. There's an OH here before it forms a bond, but it's sticking out. These guys touch, and eventually hydrogen comes off of one of these, OH off of another. It forms this siloxane bridge. So the more of these siloxane bridges you get, the higher the friction force, because you have to break these covalent bonds to slide. So we think this this forming of bonds across the interface with time is occurring, and that's why the friction is going up. Now, she's done some interesting calculations to show, why is it logarithmic? If this is just a first order reaction, why shouldn't it just be linear with time? One happens over here, and another one over there, and another one over there. Why is it logarithmic? There are two reasons. One, she discovered that there's an antagonistic interaction between a site that has reacted and then the neighbor. So if this site reacts and this one has not yet, a higher energy barrier exists in the neighboring site. So there's an inhibition to forming new neighbors that she has identified as being related to strain through the lattice. So when one bond forms, it strains, it strains the matrix such that it becomes harder to form neighboring bonds. Okay? And they've used quantum chemical calculations to demonstrate this. So the more bonds you get, the harder it gets to make more, because you start having to put ones nearby where you're at. But there's another reason, and this is a fairly generic thing, and that is if you have a distribution of energy barriers instead of a single energy barrier, then instead of getting a linear relationship with an activated process, an activated process, if you have a distribution of barriers, tends to smear out and become more slow with time. It becomes often logarithmic. The low energy barriers react first, then you run out of the easy reactions, and now you have reactions at higher barriers. So it takes more and more and more time to get more and more sites to react. So this is a plot of energy barrier distributions. This is a sort of pressure-based distribution. It starts off with mostly one reaction barrier, and then those get eaten up. Strain occurs, it modifies other barriers, and the final distribution of energies is broader. And if you look at the concentration of bonds versus time, it starts off like this, and then there's an extended logarithmic regime, and then it saturates. And this matches the experiments fairly well. Okay, so over this range from 1/10 of a second to 100 seconds, she sees a linear growth of bonds with time. We see over that same time period a linear growth of friction with time.
Have you ever seen this situation?
So we've tried. You can see the problem here. You see how these data points are spread out? The reason is it's very hard to hold an AFM tip steady for 100 seconds. There's drift in the system, and if it drifts, it might start to slip. So we've worked on this. It's not impossible, but we're trying to use feedback and force control to control the position so we could try to saturate. So we haven't seen it yet, but that's one of our goals, immediate goals, actually. But, in fact, that's a great, oh yes, Aran.
Logarithmic behavior is obtained for a specific distribution of energy barriers, or is it generic?
I'll get to that. It's not universal or fundamental, but it's fairly generic in that, and I think Shmuel has seen this in some of the work he's been doing, that when you have a spread of some kind, and I'll show you a bunch of examples, you tend to move toward logarithmic. And if it's a flat distribution, you can mathematically derive it's logarithmic. So if it's a uniform spread over a wide enough region, it's log. And then in something non-uniform, it's close to log. I'll show you some examples. Actually, it's a more generic phenomena. If it is an Arrhenius-like behavior, okay, yeah, then when you have an activated process, Boltzmann factor, you put in a distribution of barriers and integrate, you get a spread in the kinetic behavior with time.
Isn't this the new thing that Coulomb found?
the new thing that Coulomb found.
Because the other stuff attributed to him had been found many times before, but I think
Yeah.
this logarithmic aging was actually Coulomb's genuinely novel contribution.
He did look at speed dependence, but I wasn't aware that he had talked about the log behavior.
I think so. I think he held things up to a year.
Ah,
It's
okay.
easier to hold a ship in place than an AFM tip.
Yeah, right. It is seen in a wide variety of materials. It's seen with paper, it's seen with sand, it's seen with glass, it's seen with polymers. So this linear logarithmic behavior with time is quite widespread, and this is one way to explain it, is distribution of barriers.
Many of these other materials that you mentioned are creep.
That's right.
Clearly visible. So can you explain why?
Yeah.
Maybe get to
So creep also tends to be a logarithmic process, and that's one of the reasons why it's the alternate popular explanation for aging. And we're not ruling out creep in the geological systems. There almost certainly is. The stresses are very high. We know that our experiments don't have creep, and the reason is, one, we image the tip before and after. It hasn't changed. We image the surface before and after. It hasn't changed. We change the chemistry of the surface, and the behavior does change. The plasticity shouldn't change with that surface chemistry, but this mechanism should, and it follows that.
And did you also try to change the roughness?
We have, not that systematically, but we sort of, there are samples you can have that are somewhat more rough, and we don't see a strong dependence on that. And I think it's because we have such a tiny contact area. That might change if we had a larger contact where you were sampling multiple contacts and changing the stress distribution. Yeah, there was a question over here.
So, having done fluid dynamics and dimensional analysis too much, should I be worried the force doesn't have the units of long time?
So let me show you what happens. Well, one is in the empirical description. Of course, you have a speed and you have a memory distance that is used to for taking the log. So there's some intrinsic time that you use to normalize this. So, but that's which is subject to a lot of debate as well. This is an empirical relation. But
what about the normal force, the linearity with normal force of the
so okay, I wasn't going to talk about that today, but in fact we have measured over a range of normal forces, and that's new results that we just published this year, and the behavior persists. So the friction force goes up, but the linearity persists, and that suggests that the stress dependence of the energy barrier distribution is rather weak. Okay. So the behavior is fairly robust over a fairly wide range of loads.
Can you estimate the amount of bonds you form over time?
I beg your pardon?
Can you estimate
The
surface percentage of the bonds that you form?
the number of bonds that we form. So in fact, in the calculation, so again, this is Isabellas Sufarska's calculation. This is the percentage here of the total number of bonds at the interface. So you can see they are saturating, and they're getting close to 100%. So the logarithmic regime that they're matching to our experiments is going from about 10% to 75%.
Can you measure it? I mean, if you hold it in place and then try to
Yes. So we do that, and we do see that the longer we hold, the longer the higher the adhesion force is as well. There's a lot of scatter in adhesion, and the reason is if you don't pull off perfectly normally, but if you have a little bit of tilt, you can de-adhere earlier than you should. It's challenging to make it perfectly normal, but generally, yes, we see a strong increase in the adhesion force with the hold time as well. So Iran's there was a question over here.
No, okay. Probably we go to questions because otherwise
I will run out of time. But I'm delighted by the interest in this. It's just a good thing. This is what we want. This is discussion that Jay is always so good at. So this was new from Isabella's group. What's new, and this is what we haven't published yet, is the flip side of Iran's question. He asked, can we go to saturation? No, but what we figured out was how to go to smaller times. And there should be a deviation from the log behavior at small times, and indeed we see it. So here's the log of time. And so this is down to about 5 milliseconds or so of hold time. We can control the time pretty precisely in the AFM, and what we see is that it deviates from log, and the reason and the deviation is pretty much linear. So we see a linear increase in friction initially, and then it turns into a logarithmic behavior with time, this friction drop. And we see stick-slip behavior, and I won't, if I have time at the end, I'll say more about the mechanism of this, but the stick-slip actually helps us in a very practical way. If you stick here for a very short amount of time, that's a tiny hold experiment. It's holding with shear, but you're holding for very small intervals. And the stick-slip amplitude and period depends on your pulling velocity. And this force that you get drops logarithmically with speed. But before I go into the mechanism of that, let me just say the practical consequences. You can use the stick-slip to complement these static hold experiments. So I just showed you this data, log here, linear here, slide, hold, slide. If we do stick-slip experiments and analyze the stick-slip data, it falls, again, right on top and down to about this point here. Oh, I'm sorry, I'm saying it backwards. This is slide, hold, slide here, and then this is stick-slip experiments here. So we see a consistent trend of this deviation at low times. Why is it deviating at low times? Okay, here's Isabella's calculations. They make an energy barrier distribution. In this case, this is a pressure distribution. You have, most of the sites are not in contact, and so you have some energy barrier for these sites. A few of them have positive pressures, a few of them have negative pressures. The pressure is hypothesized to affect the energy barrier of this condensation reaction, okay? And so you get some increases in energy barrier, some decreases in energy barrier, and forget about the blue line, look at the red lines. The concentration of species and the friction force that you predict from that has a slow behavior, and a linear behavior initially, and then there's this log behavior. Let me plot it linearly versus time. This is the friction. Very rapidly, you get a jump. That's because the low energy barriers react right away. So boom, a whole bunch of bonds form. And then you get this slower increase with time. If they change the energy barrier distribution, so I think Aran was just asking about this. So here's an energy barrier distribution they predict if they do a molecular dynamics simulation of the two slightly rough surfaces in contact. You get this distribution. You also get a log behavior, but the starting up, the ramping up is different because you don't have a large number of low barrier sites. You have to go to higher energy barriers. So there's a slower turn on of the bonding and slower increase of friction with hold time. So these are some of the differences at early times that happen, even though at the middle times it's still logarithmic. Then here's another distribution. Here's the uniform pressure distribution. It actually looks almost purely logarithmic the whole way through, okay? Fairly rapidly at first and then. So you can actually fit the data to this. And this is data that her former postdoc produced just this week. We'd been when postdocs leave and get jobs, it takes a while to get them to produce data. So he had produced this. This is, if you do this, a delta function distribution, everything at the same barrier, yeah, there's some logarithmic behavior here, but it doesn't fit the data at the small time scales. And I'm sorry you can't see this. This is the low time scales from 1 millisecond to 100 milliseconds. Whereas if you do this pressure distribution where you have a concentrated energy barrier with tails because of adhesive and compressive pressures, you get a nice logarithmic fit. You get linear behavior that fits reasonably well. So the short story of all of this is aging is logarithmic, but not at short times. And we can see that deviation. And that matches calculations for this chemical bonding mechanism. Okay, so gives us further confidence that this chemical bonding is what's happening, and it does interesting things at short times. Maybe just in the last minute. Okay, question. Pardon me? Well, so we had it was a uniform distribution within an upper and lower bounds. Okay, and it looks very logarithmic. If it's sufficiently wide, then that's what you see. Okay, and then the last new thing, again, which we haven't published yet, so I'm happy to share and get your feedback on. This is Stickslip data. If we go fast enough, we see the Stickslip. It has a load dependence, so the black is at lower load. You can see it has a lower Stickslip amplitude. The red is higher load, higher amplitude. And if that's what happens if you change the load, so more aging, higher static friction. The friction as you stick during each phase is higher. And then if you change the speed, so here's going faster, 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 faster. And I'm sorry, ignore this. If you change the speed, you have shorter hold times while you're sticking, and eventually you get to smooth sliding. So just spreading those data points out, here's what it looks like, 8 nanometers per second up to 2,600 nanometers per second. So this is just the initial static friction peak from some holding that happened. But the take-home message from this, first of all, is this chemical process is extremely well-behaved. So it's just a small tip, yet every time you stick, you get almost exactly the same static friction force. So it's a very well-behaved process. So what we think then is that you can explain this bonding as a function of time with a smooth curve like the ones I was showing before, these ones. You know, this like this, bonding versus time, and friction, static friction versus time. So we can make an explanation for this mechanism by going back to the 50s. This is, Rabinowitz had this wonderful paper where he talks about the mechanism, the intrinsic variables affecting the stick-slip process. So here's your static friction force versus time. So if you look at this red curve here. So this is the force you need to slip as a function of the time that you hold. And then if I start here at time t equals 0, and let's say I have a weak spring, then this will be my force versus position. And as I pull and pull and pull and pull, the contact is aging, okay? And the weaker that spring and the lower the velocity, the longer it takes before I reach the static friction, and then I slip. And then the system resets itself, and now I've got a fresh contact. The friction goes back to the starting point, and it starts to age all over again. I start to pull all over again, but I'm at a higher force than before because I didn't slip all the way down. And so now I slip a little earlier, and then you go through this cycle, okay? So this is Rabinowitz's map to follow how the stick slip goes. So this is what happens if you go slow. This is what happens if you go fast. And that's what you see here. Slow, more time for aging, fast, less time. And if you track this, you can get a plot of that force versus time, which matches reasonably well with these curves we were showing for the friction or the number of bonds versus time. So let me wrap up. So we see this logarithmic increase with time. We think it rules in this chemical aging mechanism. We see that it's consistent with the distribution of energy barriers. And we see linear aging at short times because there's this burst of non-interacting low barrier sites early on. And we see aging effects in the stick slip behavior. It's the underlying cause of the velocity dependence of the stick slip. which shows that, that it's well behaved and the fact that you're shearing has relatively little effect on the aging itself. I didn't discuss the load dependence or the memory effect, but we have some work on that, and I welcome your questions. Thank you.
I think that there is an aspect that is always often neglected. That is, and well, this is true, for example, clearly in humid atmosphere, which is the time of formation of the liquid bridges.
Yes.
And okay, I agree with the fact that you have chemicals, especially if you use a silica outside. So that is certainly true. But there is something which is still important from a statistical point of view, which is the distribution of the formation of the liquid bridges.
Right.
And actually, many years ago, 20 years ago, we published a paper in which if you do that with hydrophobic surfaces, actually these effects totally disappear because there is no contribution of the time of formation of liquid bridges.
Yeah.
Okay, that's what my conclusion.
Sure, I think that makes sense, and in fact, we see a humidity dependence, and in dry conditions, the aging is greatly reduced. Interestingly, at very wet conditions, the aging is also reduced, and we think this is because you now have pretty much a flooding of the contact. There's a water film everywhere. You don't have any more adhesive forces from that, and you make it harder to produce water in this condensation reaction. So we see this non-monotonic.
Okay, my question is related to short time
Yeah.
behavior of aging. I guess in your slide experiments, actually at small time, your tip is not really at rest. You know, it still continue to slide. You can easily estimate this characteristic time for this, and this can also influence short time behavior.
Yeah. So we were concerned with that. The nice thing about the AFM is that you have it's small, and so you have very good time resolution. So the resonance frequency of the cantilever for its lateral motion is in the hundreds of kilohertz regime. And our data acquisition can keep up with that. So we can actually resolve if it's moving or not down to much smaller times than a millisecond. We can go into microseconds and regimes. So we're actually quite confident that there's no relative motion between the tip and the sample when we're holding at the level of milliseconds. Milliseconds is pretty slow for us. So the thing you might have, though, that is harder to control is you might have ringing. You might have strain going on. But we can be confident that there's no slip because we can resolve those slips and we can see the cantilever's motion.
Any comments on broader impacts? What are some
Yeah.
things you can do when you understand this?
Right. So we think that this is strong evidence that chemical bonding is occurring in silica-based materials, and silicates dominate the lithology of crustal rocks. And our geoscientist collaborator, David Goldsby, has been doing laboratory-scale rock friction experiments to try to make observations to see these silica-like bonds. And there's evidence in the literature already in support of this. What we've got here is more kinetics and time dependence that we can use to fit that data. So we think it can add to the ability to predict when slip will occur.
Just a quick question, getting back, I guess, to Dan's question about the scales. So we've done some experiments about 5 years ago or so, where we looked at aging and started aging. And we found that, okay, you need a time scale to log. What can you do?
Yeah.
And it comes basically, in our experiments, it came from the slip velocity right before the thing stopped, divided by the characteristic
Yes.
scale of the bump.
Yeah.
But that actually gives you a functional form. It gives you a constant plus. I wonder if it might be different reasons, but whether it fits to this data or not.
Yeah, I think it does in that, but for a different reason.
Well, you have a time scale of it.
Yeah. So we have a velocity at which we're pulling, and there is a distance we need to slide before the contact, memory distance essentially, before the contact refreshes itself. And we think we can get at that because we can see that there's a time at which, there's a time scale at which the kinetic friction stops going down. So initially, friction versus time goes down with the log of sliding velocity. And that's because you're giving less time for aging. And then eventually that bottoms out and it starts coming back up again. And so it's coming back up because you now have this thermal effect. You have a rate effect. And so we think that that's gives us a transition velocity, and we have the time at which this saturates. I'm out of time. Speaking of time, so we'll talk about that later.